Welcome to today's Explainer. We're jumping right into the incredibly complex, completely fascinating physics and engineering behind high-frequency transistors. If you've ever wondered how military radar systems track targets with such pinpoint accuracy, or how satellites maintain crystal-clear communications across the sheer vacuum of space, well, the answer is actually hidden in a microscopic piece of technology. Today, we're demystifying the metal-semiconductor field effect transistor, the MESFET. We'll be looking at the extreme environments these devices operate in, the specialized materials that make them tick, and the microscopic battles engineers fight every single day to keep them running. Here is our roadmap for today. First, we'll meet the MESFT. Then we'll explore why materials matter. Third, we'll look at real-world microwave applications, followed by the sub-micron scaling challenge. Next, we're battling extreme temperatures. And finally, we'll unpack the dual-gate solution. Section 1. Meet the MESFET. Let's see exactly why this device is known as the high-frequency heavyweight. We are talking about staggering performance here. These production devices operate at speeds up to 45 gigahertz. To put that into perspective, they absolutely blow traditional silicon-based junction field effect transistors, or JFETs, and standard MOSFETs right out of the water. When you're dealing with microwave and radio frequency applications where extreme frequency handling is literally a make-or-break requirement, this is the exact benchmark you have to hit. So what makes it so fast? Well, the fundamental difference is that a MESFET bypasses your standard PN junctions entirely. Instead of a traditional setup, it uses a metal-semiconductor junction, which is specifically called a Schottky junction, to control the flow of electricity. Think of this metal gate as an ultra-responsive control valve. It allows the device to switch signals at those breathtaking 45 gigahertz speeds, completely avoiding the lag that traditional semiconductor boundaries usually create. Moving to Section 2, Beyond Silicon, Materials Matter. Let's check out the specialized alternatives that actually make these speeds a reality. Now, what's really wild about this architecture is what's missing. While a standard MOSFET has a protective insulated shield sitting right over its active switching region, a MESFET doesn't have an insulator under the gate at all. Because of that, it has to rely on a very carefully managed, reverse-biased depletion zone to function. It acts like an electrical roadblock. If you don't keep that gate reverse-biased, the whole thing could accidentally turn into a forward-conducting diode. And that is one heck of a design constraint for engineers to work around. To make this very specific architecture thrive, engineers have to ditch standard silicon and turn to compound semiconductors like gallium arsenide. By using gallium arsenide, we get an electron mobility that is a massive 6 times higher. That means electrons literally rip through the channel with a fraction of the usual resistance. That right there is the ultimate speed advantage you absolutely need for ultra-fast digital integrated circuits and microwave frequencies. Section 3, Real-World Microwave Applications. So how does this actually power our global infrastructure? You'll find these devices working behind the scenes in some incredibly high-stakes environments. From keeping satellites communicating in orbit to powering critical military radar, MESFETs are the hidden engines of our modern world. They often act as front-end low-noise amplifiers and microwave receivers. Basically, they can take an unimaginably faint signal bouncing off a radar or beaming down from space and amplify it without adding a bunch of electronic static. Now, because they are more expensive to produce than standard silicon, they're reserved for the heavy-hitting jobs, like microwave-linked power amplifiers and commercial optoelectronics. Section 4, the sub-micron scaling challenge. Let's start shrinking things down to the atomic level. If we zoom way in and look at a cross-section of the two-dimensional geometry we're dealing with, you'll see a metallurgical gate measuring an incredibly tiny 0.3 microns in length. Just beneath that, you have the N-type doped channel, which is sitting right on top of a semi-insulating gallium arsenide substrate. We are talking about a structure where the active channel is just fractions of a micron thick. The tech industry's constant mandate is always make it smaller, make it faster, make it more integrated. But as we aggressively shrink that gate down to 0.3 microns and below, we really have to ask, how does the physics actually hold up at this microscopic scale? Well, things get remarkably messy. Shrinking introduces what we call short channel effects. These can severely bottleneck device performance because they mess with the output conductance and transconductance, which is really just a fancy way of saying they ruin the gate's ability to effectively control the electrical current. And here is where it gets even more complicated. The older mathematical models we used to rely on completely break down at this size. The classic Curtis and Rodriguez models, they can't simulate how threshold voltage depends on drain and gate voltages at this scale.
The Materica-Casaprac model, its accuracy takes a nosedive as the device gets smaller. And the Tajima model entirely fails to simulate output conductance and transconductance. Engineers literally had to invent brand new, temperature-dependent analytical models from scratch just to understand how these submicron devices behave.
Which brings us to Section 5, Battling Extreme Temperatures. Surviving the heat at a microscopic level. Picture this. Researchers are stress testing these advanced devices up to a blistering 900 Kelvin. That is over 1100 degrees Fahrenheit. When you push high drain source voltages, specifically anything over 1 volt, through these tiny submicron channels, the electron temperature completely decouples from the lattice temperature of the surrounding material. In simple terms, the electrons themselves get boiling hot where the physical material around them even has a chance to catch up. So how on earth do they survive that kind of intense heat without just melting into useless slag? Enter gallium nitride. Gallium nitride features a tremendously wide band gap of 3.47 electron volts at room temperature. This wide band gap means it takes a massive amount of energy to force electrons out of place. It provides a huge thermal advantage over standard gallium arsenide, essentially stopping diffusion-dominated leakage currents dead in their tracks, currents that would otherwise completely destroy a silicon chip at those extreme 900 Kelvin temperatures. Finally, Section 6, the dual-gate solution. Let's see how engineers build their way around these limits. So we have overlapping problems, right? Extreme heat, high voltages, and those pesky submicron short channel effects. How do we solve them all at once? The trick is adding a second gate. By placing 2 independent gates between the source and the drain, you essentially create a cascade connection of 2 single-gate transistors working in tandem. You are structurally separating the responsibilities of the device between FET 1 and FET 2. This dual-gate setup is an absolute masterclass in device engineering. It's the structural solution that lets us keep shrinking the technology without breaking the physics. This cascade configuration vastly improves overall output impedance. It drastically reduces feedback capacitance, which means a lot less internal electrical pushback, and it actively squashes those short-channel effects that plague single-gate models. Best of all, it does the whole shebang while maintaining total stability at high operational temperatures. It's truly a game changer. As our global demands for high-power, high-temperature microwave electronics continue to skyrocket, the MESFET is going to have to keep evolving. I really hope this explainer sparked your curiosity and gave you a new appreciation for the invisible, atomic-level battles happening inside your high-speed tech every single day. Because it leaves us with one massive question. As we relentlessly push for smaller devices and even hotter environments, what radical new semiconductor architectures will we have to invent next?